So in this video, we're going to talk about how to compute moment of inertia using integration, along with what the basic definition of moment of inertia is and why it's important. So if you think back to chapter 7, when we were analyzing beams, for a given load, we know how to determine the internal stresses of that beam, assuming that it's loaded correctly, only perpendicular to its span. Those will only be a shearing stress and a bending moment. And not only do we know how to find them at a particular point through the method of sections, but through those diagramming techniques that we spoke of, we know to find out how they vary across the entire beam. So once we know the actual bending moment particularly, that's a really important parameter for a beam because it determines the tendency of that beam to actually deflect, which is a bad thing, obviously, from a structural engineering perspective. So if we want to, knowing the actual bending moment that we have to tolerate for a given load, try to minimize deflection, what it really comes down to is how do we design the cross-sectional area of the beam? Remember that beams, by definition, oftentimes have a uniform cross-section throughout their entire span. So if you think about it, without knowing anything about strength of materials, you might assume that the more cross-sectional area, the less a beam will deflect for a given load. So looking at A, B, and C here, they all have the same cross-sectional area, 30 centimeters squared. But if we were to build a beam with all three cross-sections and subject it to an actual load and measure deflection, what we would find is that deflection is minimized for cross-section A, which is called an I-beam cross-section. If we compare the geometries between A, B, and C, we notice that what's unique about A is the majority of the area seems to be spread away from the midline. And what we're going to talk about in this chapter is that the moment of inertia is actually a metric that will be large for areas that are spread away from a midline. And the reason that is because it's actually computing the second moment of an area about an axis. So long story short, when we go to the next slide and formally define moment of inertia, just know that it's a property that tends to correlate with how less a beam will deflect for a given loading. So the moment of inertia is computed using what's known as the second moment of an area. So if you look at these two equations here, moment of inertia about the x-axis is Ix, moment of inertia about the y-axis is Iy. Notice that we're integrating a product of area times a distance squared. And in the case of the moment of inertia about the x-axis, which would be horizontal, that distance is measured in the vertical direction. So it's perpendicular from the actual axis. So if you think about that example that we just did, if we chunk up an area into infinitesimal areas, we measure their distance rather from that axis, we square it, and then add all those up. This will be a measure that increases as the amount of area separates away from that axis. So that's kind of why the I-beam has such good properties with respect to minimizing deflection. If we think about the units of moment of inertia, since we're taking the square of a distance in the integral along with the area, it will be in units of length to the fourth power. Another term that's good to know is that in addition to measuring kind of linear moments of inertia about your horizontal and vertical axes, you can actually define a polar moment of inertia, J0, which is related to those linear moments as you see in this equation. So from a computational perspective, at least when we're trying to determine via integration what these moment of inertias are for a complex shape, it's going to look a lot like the problem of determining the centroid of a shape, because the only thing that is different within the integrand is this argument y and x is raised to the second power instead of the first power. So let's actually see how we would go about doing that. We have a complex shape here where the upper side is bounded y as a function of x cubed by a cubic, and what we're trying to do is to determine the moment of inertia about both the x and the y axis. So very similar to what we did for the case of the centroid, we're going to segment this complex shape up into rectangles under the idea that we know the moment of inertia of that little chunk, and we're going to add up the moment of inertia of all those little chunks via integration. Now, typically when we have y bounded as a function of x, we use vertical rectangles and we'll actually integrate over x. So what we're going to need to know is what the moment of inertia of this little rectangle is about both the y and x axis. So in the case of the y axis, probably not surprising to you, the infinitesimal moment of inertia, diy, is simply x squared. Notice that for an infinitesimally thin rectangle, that's simply the perpendicular distance from the y-axis to that rectangle times the area. And we know that the area is going to be our dx times whatever y is. So if I want to find the total moment of inertia about the y-axis, all that I need to do is to sum those in the infinitesimal sense, which is why I'm basically just integrating. How can I write an expression for the infinitesimal area, dA, as a function of the actual variables, y and x? Well, dA for vertical rectangles is always just the height, which is y, times the width, which is dx. We can express y as a function of x, which we want to do in order to make this a single integration problem, using that formula that we were given, h over b cubed, x cubed. And then if I substitute those in to the actual integral based upon this formula that I have at the top, we notice that even though it looks complicated from an algebra perspective, this just basically becomes a simplistic power integral. Namely, we have the constants h over b cubed, which can come out of the integration. We're integrating x to the fifth. And remember that the antiderivative of a power function is simply that another power function where we increase the power by 1 and divide by that new power. So x to the fifth, antiderivative, increase the power by 1, 5 becomes 6, divide by 6. That's where they're getting the x to the 6 divided by 6. If we evaluate that from the upper limit of b to the lower limit of 0, we get an expression for the moment of inertia about the y-axis, which is just 1/6 b cubed h, and it just looks like alphabet soup because all of the dimensions and the function are, of course, expressed in terms of those kind of constants b and h versus actual numbers. But if we were to actually kind of put a relative number on the, or I should say an absolute number on the moment of inertia and compare it to another shape, we would see that this should have a relatively large moment of inertia about the y-axis because a lot of that area is far away in the perpendicular sense in the horizontal direction. So how do we actually go about determining the moment of inertia of this complex area about the x-axis? Well, this is going to be a little bit harder because first we have to determine what the moment of inertia is of just a little infinitesimal rectangle about the x-axis. So remember, in the case of the centroid, it was just the intersection of the two lines of symmetry, or right at the middle. It was y over 2. But here, what we find is that through table lookup, and you don't need to worry about how this is actually derived, that the moment of inertia of this little rectangle about the x-axis is 1/3 y cubed dx. So if I want to find the total moment of inertia about the x-axis, what I'm going to do is just to add all those up via integration. That's all that's being shown here. Notice that, of course, since we're integrating in x, we need to express y as a function of x, which is what they've done here. Be careful that you're cubing all of y, so that both the constant and the variable to the third power need to be cubed. And when you raise a quantity that has a power to it to another power, remember that those exponents multiply. So that's how they're getting the 9 in this case. Follow through your integration, and you will find that the moment of inertia about the x-axis is 1/30 bh cubed. So what you generally see, one thing I wanted to emphasize out of these two slides, 6 and 7, that's going to be important in our next example, is that it's generally easier to compute the moment of inertia about an axis if you break it up into rectangles that what's a good way to say this, that slide away from that axis. So here's what I mean by that. In the case of these vertical infinitesimal rectangles, it was very easy to determine the moment of inertia about the y-axis because the infinitesimal moment of inertia was just y squared. If we go back to here, sorry, I should have said x squared. I was pointing in the right way, but not saying it, x squared times dA. Versus when you tried to determine the moment of inertia about the x-axis, you had a little bit more complexity. So long story short, we're going to like to, when we're trying to find the moment of inertia about an axis, say it's the y-axis, we want to break it into vertical rectangles. If it's the x-axis, we want to break it into horizontal rectangles. That way we can have this kind of easier setup that doesn't require on memorizing or looking up that formula for the case of determining